Hi everyone, I'm Wen Xiao from the University of British Columbia. Today I'm going to present our paper, Systematically Exploring Redundancy Reduction in Summarizing Long Documents. The work is done by me and my supervisor, Giuseppe Caronini. First, what is extractive summarization? It's a task to select sentences that can best represent the whole document, and it can be regarded as a sequence labeling problem, with one meaning the sentence should be selected and zero meaning not. As shown in this example, for this news article, the second and fourth sentences are selected to represent the whole document. What is a good summary then? It should be informative, which means it should contain adequate information from the original document. It should be salient, which means it should capture the core information. And it should be non-redundant, which means it should not be repetitive. Previous neural models focus more on the informativeness, and in this work, we aim to reduce redundancy while keeping the informativeness in the generated summary. Now that we want to reduce redundancy, then how can we measure it in a given document? We use two automatic metrics to measure the redundancy. The first one is unique n-gram ratio, which measures the n-gram uniqueness in the document. It is computed as the number of unique n-gram over the total number of n-grams. And the second one is normalized inverse of diversity. It is based on the diversity of a document, which is defined as the entropy of unigrams in the document. The higher NID is, the more redundant the document is. Equipped with these two metrics, we evaluate the degree of redundancy of the documents in the four popular summarization datasets: CNN, Exam in the news domain, and PubMed Archive in the scientific paper domain. Here in the table, we show the basic statistics of the four datasets with number of documents, average length of the document, average length of the sentences, and the NID score, the unique unit by and trigram ratio. From this table, we can find that the scientific paper tend to be much longer than news article, and redundancy is a more serious problem in scientific paper. Also, the sentences in the scientific paper datasets tend to be much longer than news datasets, which might make redundancy reduction even harder for extractive summarization in the scientific paper dataset. So in this paper, we focus only on the scientific paper. Now that we have the task and data, what would be the model like? Here is the common framework of neural summarizer. It contains two phases. The first phase is sentence scoring phase, in which an important score would be assigned to each sentence by a neural model. And in the second phase, sentence selection phase, we select sentences based on its importance score and or other measurements. Based on when and how the redundancy is considered, we organize the redundancy reduction methods into three categories. First, when designing the neural architecture, we implicitly take consideration of redundancy. And second, when compute scores for sentences, we explicitly consider the redundancy. And third, when selecting sentences, we explicitly deal with redundancy. Before jumping to the exploration of redundancy reduction methods, we first introduce two baseline models we use in this work. The first one is naive MMR. It is a traditional extractive summarization method, and it ranks the candidate sentences with a balance between informativeness and redundancy with the balance factor lambda. As you can see from the equation, the first term represents how much information the sentence contained, and the second term measures how redundant the sentence is compared with the previous selected sentences. The second baseline model is X-sum-LG. As we want to compare redundancy reduction methods, we need a fair test bed. We choose this model because first, it is the state-of-the-art summarizer on both scientific paper datasets. And second, it is a non-autoregressive model and it doesn't consider redundancy aspect. Here we show the encoder, decoder, and loss used in the sentence scoring phase. And as for the sentence selection, we just greedily pick top K sentences. Here we summarize the baseline models. The naive MMR use cosine similarity to measure the importance of the sentences and take consideration of redundancy in the sentence selection phase. And the X-sum-LG model uses own encoder, an MLP decoder, and cross-entropy loss to score sentences. Use greedy algorithm to select sentences. Now, I'll talk about the two methods in category A. Both of them are from previous work and use autoregressive decoder. But different from sum-runner, the new sum decoder learns the relative gain step by step and use KL divergence as the loss function. In the sentence selection phase, both of them select sentences greedily based on the score. The details can be found in the paper. Still to summarize, the two methods in category A mainly change the decoder as an autoregressive decoder. There is only one method in category B, which is called RD loss, proposed in this paper. It simply adds a redundancy loss term LRD to the original loss. And it explicitly learned to reduce the score of redundant sentences. As you can find from this equation, if the similarity between SI and SG is very high, then it just punish the score on YI and YJ. To summarize, comparing with the original baseline model, the only change made in the RD loss method is adding a redundancy loss term in the loss function. Finally, let's talk about the methods in category C. The first method in category C is a simplified version of MMR with a hard constraint. It has been used in many summarization models, like birdsong. In the sentence selection phase, the current candidate is selected only if it doesn't have trigram overlap with the previous selected sentences. Otherwise, the current candidate sentence is ignored and the next one is checked. The method works well on the news dataset, but the hard constraint might not be a good choice for the scientific paper, as the technical term is usually long phrases, and the core sentences usually repeats those terms. Thus, we propose a new method, MMR select. It balances the informativeness and redundancy in a soft and flexible way. The difference between this method and naive MMR is that it uses the important score of the neural model to represent informativeness, while it's the cosine similarity between each sentence and the document in the naive MMR. Based on MMR select, we propose another method, MMR select plus, which is to promote synergy between sentence scoring and sentence selection phases. In addition to using MMR select in the sentence selection phase, we also fine-tune the trained neural model in the sentence scoring phase. It combines three components: the neural model, the original cross-entropy loss, and the new RL mechanism whose loss is LRD. Zoom in the new loss term in the RL mechanism. It is the inverse expected reward based on the root score of S hat generated by MMR select, weighted by the probability of the Y hat labels in the log space. We adopt the self-restriction strategy by adding a baseline summary S bar, which is generated by greedy algorithm on PY. In this way, it only positively rewards summaries which are better than the baseline. To summarize the three methods, all of them use a different student selection algorithms. In addition, the MMR Select Plus fine-tune the neural model based on MMR Select. Now I'll talk about the experiments. We use PubMed and arXiv as the datasets, and use root scores as the metric for informativeness, and use the two measurements we mentioned before as the metric for redundancy. Before go through the overall performance, let's explore the informativeness and redundancy. Recall that the MMR Select is designed to balance between informativeness and redundancy. Then what the balance factor should be? We did experiments on the validation set, exploring the informativeness and redundancy with different weights. First, consistent with previous work, we find there is a trade-off between informativeness and non-redundancy. And then we found an upper bound on how much the generated summary can match the ground truth summary. But the redundancy continued to increase. It indicates the necessity of applying redundancy reduction method. Now, let's look at the performance of different methods on redundancy. The first block are the results of baseline models. The second blocks are the results with redundancy reduction methods. And the following two blocks are oracle and reference respectively. Green means it is better than the XSUM LG. Red means worse. The dagger note represents significantly better than XSUM LG with p-value less than 1%. From the table, we can see trigram blocking makes the largest improvements on redundancy reduction. And almost all the methods can effectively reduce redundancy, except for SR decoder. By injecting the RL mechanism, the MMR Select Plus works better than MMR Select, especially on the PubMed dataset. As for the informativeness, the three new methods can reduce redundancy significantly, while also improving the informativeness significantly. And both trigram blocking and new-sum decoder effectively reduce redundancy but hurt the informativeness. Contrast with the experiments on the news dataset. Compared with MMR Select, MMR Select Plus works better on both redundancy and informativeness aspects. So, to sum up, we find that longer documents tend to be more redundant by examining large-scale summarization datasets. And we systematically explore and compare existing redundancy reduction methods in extractive summarization for long documents. With the new redundancy reduction methods, the new model beats the original state-of-the-art model on both informativeness and redundancy. For future work, we want to do experiments with generating summaries at finer granularity than sentences, such as subsentences, EDUs, and we want to explore the methods on short documents as well. When considering redundancy in the loss function, we want to use a pre-trained neural model to compute the similarity between sentences instead of cosine similarity. And in addition, we want to do a human evaluation in addition to the automatic redundancy metrics. That's all I want to present today. Thanks for your listening.